In section 5.6, we're going to be looking at the rational root theorem. The rational root theorem basically gives us a way to determine the number of possible roots of a polynomial equation p of x equals 0. So if the coefficients of p of x are all integers, then every root of the equation can be written in the form p over q. And what p and q represent here is that p is all the factors of our constant term, and q is all the factors of our leading coefficient. So let's look at an example, and this might make a little bit more sense. Here I want to find all of the rational roots of p of x equals 2x cubed minus x squared plus 2x plus 5 equals 0. So I want to kind of find all of my p over q terms. So how I'll do that is first I look at my constant term, which is 5. The factors of 5, since this is prime, are just plus or minus 1 and plus or minus 5. So those are my values for p. Now I want to look at my leading coefficient, which is 2. This is also a prime number, so the factors here are just plus or minus 1 and plus or minus 2. And what I care about here is my p over q values. So any combination of p over q is what I'm going to be using here. So my possible roots could be at plus or minus 1 over 1, or just 1, plus or minus 1 over 2, plus or minus 5 over 1, or that's just 5, and then plus or minus 5 over 2. And what I'm going to do here, and this is going to seem kind of long, a little bit excessive, I'm going to write out all of these values. So 1, negative 1, negative 1 half, negative 5, positive 5, negative 5 over 2, positive 5 over 2. I'm going to plug those all in as an input and then see what that polynomial spits out. Okay? So when I do that, I'm going to get all these different values, and the one that sticks out to me is negative 1 and 0. Because I'm caring about whatever input I'm plugging in, I want to see if any of them will spit out 0. I see that that happens at negative 1, so I can conclude that my only rational root here is negative 1, or is at negative 1. The last thing we're going to talk about today is the conjugate root theorem. So if a polynomial p of x has rational coefficients, then irrational roots that have the form a plus the square root of b and imaginary roots come in conjugate pairs. So what that means is that if I have a polynomial and I figure out that a plus the square root of b is a root, then a minus the square root of b would also have to be a root. Similarly, if a plus bi is a root, then a minus bi would have to be a root too. And you've already kind of seen this when we've worked with the quadratic formula with imaginary and with rational numbers. Whenever I do the quadratic formula, I always get like a number plus or minus whatever's in the square root. I never just have the positive one or just have the negative root. I always kind of have both of them together in a pair. So in an example here, a quartic polynomial has rational coefficients. All I know is that positive square root of 2 and 1 plus I are roots. Just looking at that, what would the other two roots have to be? So I have positive square root of 2, 1 plus I. So the conjugates here would be negative square root of 2 and 1 minus I. So I could conclude that those would also have to be roots of that polynomial function.